Good afternoon, wherever you are in the world right now. I hope you are safe and healthy. My name is Randy Bell, and I'm the director of the Atlantic Council Global Energy Center. It is my pleasure to welcome you to our very first installment of EnergySource Innovation Stream, where we will highlight energy technologies that have the potential to reshape the energy sector, and we'll also highlight the people and companies working to bring these technologies to market at scale. As I said, this is the very first installment of this series, and so we'll be refining the format as we go along. We want to hear your feedback about what worked and what didn't work, so please be sure to be in touch with us afterwards. We are so pleased to have with us today Claude Letourneau, the president and CEO of Svante. He's coming to us from Vancouver, British Columbia. Claude has agreed to be Innovation Stream's very first guinea pig. So thank you, Claude, for joining us. Svante has a number of projects in place that use nanomaterials to capture carbon dioxide at scale. Claude is going to explain to us what that means, how they do it, and how Svante is going to help change the world. So in a moment, Claude will be sharing a PowerPoint presentation, full screen. My webcam will shrink, and attendees will be able to minimize my screen or move me around, whatever you need to better see the presentation. So after Claude gives his presentation, we'll come back and do a Q&A. So over to you, Claude, for the show.
Thank you, Randy. And you can see on the screen. Great. So, well, welcome everyone. Very pleased to be here this afternoon. You will learn in this innovation stream about Svante technology, the scale of our field demonstration program at customer sites, the competitive landscape of direct carbon capture, and how to kickstart what we call the carbon market to really big win. So climate change is basically one of the greatest challenges of our time. We now have reached a tipping point where we have to deal with CO2 emission going up in the atmosphere, and because the natural CO2 filters we have overloaded. Trees and ocean cannot anymore cope with man-made CO2. So we have a net imbalance accumulating in the atmosphere faster and faster, and hence the temperature rising up, as you see on that graph. So today, we store in the world about 60 million tons of CO2 with no benefit. We take natural CO2 and we take it out of the ground, we move it into a pipe and put it back into depleted oil reservoir. In order to meet our 2040 target, IEA is telling us that we need to capture and store the equivalent of 10,000 million tons of CO2. That's 10 gigatons. So where to do that? The industrial emissions represent about 21% of all greenhouse gas emission. So the plan is simple. Building materials are vital to our economy. We need to capture carbon from these production facilities while we do deep carbonization of the power sector and the transportation sector. But what to do with CO2? What if we could send it back to where it came from? This is called storage or sequestration, and capturing it from industrial plant, putting it back into the ground. We've been doing this for the last 30 years, and we're putting back CO2 in Saline Reservoir, for example, 8 kilometers deep underground and locking the CO2 for a long time in a safe way. So what about Svante? We're based in Vancouver. We have 80 people working dedicated to developing the technology that will allow us to capture CO2 at a very low cost. We consider ourselves what we call a mission critical company, and we're trying to address the challenge associated with climate change. So our end of the pipe solution can reduce worldwide greenhouse gas emission by 20% in focusing on industrial emission. We are backed by some of the largest energy producer. OGCI is one of their major investors. They represent the 13 largest energy companies with the Total, the BP, the Shell, the Chevron of the world. We have Chevron as an investor as well and Total as a partner. What's the innovation? We basically take a nanomaterial, which is a powder called a sorbent, and we engineer the material to have a high storage capacity for CO2. We then engineer the material to be able to catch and release the CO2 in less than 1 minute, compared to hours with other technology. Therefore, we have a much smaller inventory of sorbent relative to traditional technology. And then we have a unique compact machine that capture, release, and regenerate the sorbent in a single unit by rotating over a minute time. You can see on that picture on the left side, the bottom of the unit we have right now running in the field at Husky Energy. So what's the advantage? The advantage is a lower capital investment compared to traditional liquid systems where you would need very tall towers to absorb and desorb the CO2 from a flue gas. And in our case, because we do everything in one compact system and it's much smaller and it's not made of stainless steel as a very expensive material, hence the capital cost is reduced by half. So this is a picture of the demo unit that we have today working at Husky Energy in Saskatchewan. And you can see on the right side the picture of the machine itself inside the building that you see there. So I encourage you to go on our website, svanteinc.com, and you can see a video about 2 minutes about that facility. So where do we fit basically in the industrial market space? If you were to capture 10 gigaton, which is a requirement that IEA is giving us as an objective by 2040, it would cost us about $2 trillion to deploy capital plants in the industrial sector that we're in. Traditional technology for the same 10 gigaton would have to spend $4 trillion, and those are mainly focusing on power plants because of the economic of scale required to meet the cost of that industry. And then if you want to collect this thing from air, it's called direct air capture, and there's 3 companies working in that space. One of our neighbor here, Carbon Engineering, is working on a liquid-based system to do that. And Global Thermostat and Climeworks are doing it from a sorbent point of view in a similar sorbent material as we have in our industrial plane. So we spent the world about $2.7 trillion in the last decade to deploy solar and power and wind at a cost of about 2.7. So relatively speaking, you would get more bang for your buck with 2 trillion in going after 20% of the CO2 emission. So what we've done a few months ago is we regrouped 2 companies under a partnership with Climeworks, focusing on air capture for Climeworks and ourselves industrial, and basically are working and trying to take our filter, unique filter, and applying it to air capture so that we can work toward the goal of reducing the capital investment and therefore the overall cost in the range of $100 per ton, and integrating both industrial play that we do plus air capture so we can benefit from the waste energy we have from our system to lower the cost of air capture system. This is very promising for a net zero solution to our industrial partners. So this is the cost curve of the existing technology being a liquid-based system. So the gray curve you see there is the dollar per ton, fully loaded, meaning the capital cost, the recovery, plus the operating costs. And on the bottom axis, you see the plant size capacity. So this, and then our cost curve for our solid sorbent is the lower cost curve of this one, more darker one. So everybody is trying to get to about a $50 per ton objective because of 45Q. 45Q is a tax credit in the United States that allows basically to get a $50 per ton tax credit if you do storage of CO2. And then there's an application where you could also do co-storage with in a depleted oil reservoir. You get a price of about $20 from an Occidental, for example, who would be using it to extract oil. So going to $50, the liquid amine system would have to go to a plant size about of 10,000 tons per day. The reference plant that's existing today is about a 5,000 ton on a coal power plant today. So we crossed the line basically of $50 in our case in the range of 2,000 to 3,000 tons per day. much smaller plants because of the lower capex. And that's the price, basically, that's the volume of what you normally get from the industrial emitters, like cement plant as an example. So therefore, we are able to open up the application for industrial emission of CO2 from industrial plants in that plant size. But recently, in the last 6 months or so, many companies in the IT industry, like Microsoft and Amazon, have been pledging a net zero for CO2. So they're looking at planting trees, doing energy efficiencies, getting some renewable, but at the end of the day, they're probably looking, each one of them, in a range of 40 to 50 million tons per year they will have to deal with. And then direct air capture is what they're looking at as a solution. But direct air capture is in a price point of about $100 per ton. So that industry now, if you want to crack the code of the business model for the carbon management, you need to look at it from the point of view of the end user. You and I would be willing to pay $100 per ton if we had a product that we buy from Amazon that had a sticker on it that says, this is the carbon footprint of that particular product. And when you apply $100 per ton for that product, you easily get to a price that is affordable for the price of the value you're getting. But when you go down the value chain to an industrial emitter like a cement plant, every ton of cement would give you 0.5 to 1 ton of CO2. If you sell your cement at $100, it is very difficult to put a price of $50 or even $100 in doubling up the price of cement. Same thing with power plants. So I believe that market will evolve in the next 10 years. Right now, we're focusing on entering the market on the 45Q way of monetizing the CO2, but I believe it will open up a market at $100 on the voluntary price basis. The demand created by the Amazon and the Microsoft in their pledge in the next 10 years is going to be overwhelming, and then there'll be less capacity available than the demand they will create. So why are they concerned with emissions as the IT industry? You can see here that by using electricity to power the cell towers and in the data centers we all use, it's consuming the equivalent of about 2% of CO2 emission in the world because of power generation associated with it. In the next 10 years, because of the advent of 5G, it will double the power requirement of cell towers, plus the increase of data centers. That industry as a whole will be tagged with being the largest CO2 emitter as a single industry, representing 5%. Today, the cement industry has that position. So when you look in the United States at all the sources of stationary sources of CO2, there's about 2 million tons or 2 gigatons that's required to go to, and then you're going to find out that the low-hanging fruit is basically cement industry in the range of $50 to $80. So there's a conversion of a price point at $100. So we're looking now at mining, basically replacing mined CO2 in the United States, primarily in the Permian. So every black line you see there is an existing CO2 pipeline. There's about 4,700 miles of CO2 pipeline in existence in the United States. And then we're trying to find ways of having industrial emitter. All of that CO2, 68 million of it, most of it is coming from mined CO2 with no benefit for the environment. So what we're trying to do is map out basically North America. Every yellow point you see on that slide and every blue point you see on that plant. So the blue ones are a cement plant and the yellow ones are hydrogen or ammonia plant generating a lot of CO2 in their flue gas. And we're trying to connect the dots between the two. So one of the first projects we've announced recently is a project with Lafarge-Olson in the Permian, and where we're connecting with maybe less than 50 miles from an existing pipeline, a very large cement plant, and the off-taker would be Occidental, that would take the CO2 and put it back into their pipeline network. So today we have a plant running at Husky Energy in Saskatchewan, a reference plant of 30 tons per day. We are right now in the second phase of a demonstration program with Lafarge-Olson here in Vancouver, where we are installing a 1 ton per day facility. And then we have 2 upcoming projects in the next few years. One with Chevron, looking at putting a 30 ton per day plant in California at one of their refinery, not refinery, but oil and gas extraction site. And then we have this first commercial plant of about 2,000 tons per day that we're looking with Lafarge Olson, Occidental, and Total. So where are we in terms of deploying this thing commercially? We spent the last 3 years proving the technology to the scale you've seen in a last few slides. And it proved it works. We've built a small manufacturing line to make our nano filters. Now we're moving into the industrialization phase. So out of it, in about 3 years, we'll come out with a first of a kind commercial plant ready to be constructed. We'll be scaling up our machine size to the size required to make this million tons per year plant, and then scaling up the manufacturing of our filters to be able to supply the filters for such a plant. And once we've done this one, we're looking to deploy within the next 5 years after, from 25 to 30 plants of 1 million ton to get 50% market share of the existing CO2 market today in the United States, which is using mined CO2. And that's a $6 to $10 billion capital deployment just to do that. And we're tackling afterward the gigaton to the first, and then eventually the 10 gigaton that's required. So in conclusion, there is no silver bullet to a 2 degrees C less future. We need to stop putting CO2 into the atmosphere, period. And, while we do energy efficiency and renewable, one more solution needs to be added up. It's called carbon capture and storage. CCS is the most impactful mitigation option to pass on to our next generation. Open for questions.
Claude, thank you so much. And I am coming back onto video. And Claude, I think that everyone can see you as well, the man behind the PowerPoint. This technology looks to be potentially transformative, particularly for the industrial sector. Question, why did you focus on the industrial sector and not look to, say, the power sector or even potentially blue hydrogen?
Blue hydrogen is, for those who are not familiar, is a definition of using hydrogen from natural gas and then putting a carbon capture system. So for every ton of hydrogen you generate in getting natural gas to hydrogen, you get about 11 tons of CO2. So we are looking at putting capture systems on these hydrogen plants and therefore eliminating the CO2 footprint of the hydrogen. It's called blue hydrogen. People are also referring to green hydrogen as being the same thing, but you use electrolysis in doing it. But we believe that our carbon capture system will open up a much cost-productive way of making hydrogen through natural gas and carbon capture. So industrial, why? Because this is an area where it's hard to abate. And we still need steel to build cities. We need cement. And it's not about the use of fossil fuel. It's just intrinsic to the process of making the cement, for example.
Got it. Thank you. For those watching online, you can ask questions either through the chat or the Q&A, and I will get to those. We have 10 minutes to go. We already are starting to get a bunch of great questions in. So the first one from Juho Lipponen. First of all, Claude, kudos to you and the whole Svante team. What do you see as the biggest risks in scaling to industrial scale during 20 to 24? And I guess that's it ties on to a question I had, which is the timeline that you're proposing fast enough for the scale of the challenge that we're addressing?
Well, the challenge is overwhelming. As you can see, going from 60 million to 10,000 million tons is quite a bit. So we're trying to be very systematic in our approach to scaling up. These machines have to be built and last for 20 years. Our filters have to have a lifetime of at least 3 to 5 years to be economical. So we're working in demonstrating this thing. So Yeah, the biggest challenge I would say is that now we have, with the recent event of the virus, three crises we need to manage at the same time. We have the virus health crisis, which, as you can see, the world stopped breathing for a couple of months. We have the oil and gas crisis with the oil price collapsing. And this is where all the CO2 is going to go into the oil and gas doing storage capacity. So there may be pressure for them to delay some of it. And then we thirdly have the climate change, which is not going away. So I guess the challenge for us in the next 18 months is make sure we're well funded to go through those three crises.
Yeah, I want to. What are your thoughts on the oil and gas industry's struggles right now? You mentioned, and I've had a number of conversations that there are fears that some of these very ambitious, very forward-leaning net zero pledges may end up having to be slow walked simply because there's not nearly as much capital to make these types of investments. On the other hand, and maybe we're getting a little too off topic, but if you have any thoughts on it, please do answer. On the other hand, with oil and gas investment being less promising over the near term, perhaps there's a bigger market for clean energy technologies, or perhaps clean energy technologies will end up being supported by various governmental stimulus plans. What are your thoughts on those various threads of what's driving energy markets right now?
Well, yeah, it's a challenge time for the oil and gas. They are a partner. They've been a partner for the last 3 years in supporting us. They continue doing it. I spoke to senior leadership of all the major partners we work with, and I see the same commitment as they had before the crisis. So that's good news to me, and I'm very, very fortunate to be able to work with partners of that nature. In terms of the pricing and the investment to be made, I think the 45Q you have in the United States is there. There'll be some bonification of that 45Q that's going to take place in the next months, I would think, with the stimulus package. So I do believe that we have people in Washington taking care of this and making sure that that stimulus doesn't go away. And I believe also that the demand is now being created by the end user, as opposed to being compliance to an emission. It is very difficult for a cement producer to manage pushing this thing out under regulation, because they cannot afford the commodity price. But if it's a market pull coming from the consumer, driven mainly by the IT industry, I believe we will create some new partnership between industrial emitters, oil and gas, and IT industry to create this new market called the carbon management.
It's really, really interesting. We have two questions tied to the technology itself, asking how the technology works. One person asked, you said you have a solid powder, but then said it was a filter. How does that all work together? And if it's a filter, is it a polymer or polymer based?
So the powder itself is the magic recipe that basically catches and releases quickly the CO2, and then you need to disperse this powder in a very large surface area to quickly be able to catch the CO2 in a flue gas. So we take that powder, we put it on a laminate, like a thin film, and then we stack all these laminates to creating a space in between to create what we call a filter. But in reality, the filter is made out of the sorbent material.
Got it. Okay, we're getting lots and lots of questions here. One interesting one on the feed gas. How clean in terms of particulates, nitrogen oxides, carbon monoxide, et cetera, does the feed gas need to be so as not to affect the filtration system?
So we are doing tests right now at Lafarge on a cement plant. The cement is probably the worst case scenario you could think in terms of particulates. And we're measuring now the particulates, and the ones coming out in the flue gas to our system are much smaller than the gap we have in our filter. So we're not too concerned about that. The SOx and the NOx are basically impurities that typically would affect the chemistry of the sorbent material we have. But we were fortunate enough to come up with a new sorbent material that basically withstands the SOx and NOx environment that you have in the industrial emission.
Got it. We have on a totally different topic, and not technical, but policy related, a suite of questions tied to questions wondering about what other policy support you might see for this technology or other carbon capture technologies. You talked a lot about 45Q and that 45Q might get adjusted going forward. And so obviously you made the business case to work in the United States, but do you see other policy support or other mechanisms for funding this type of projects outside of the United States?
Yeah, of course. So Canada, my homeland, they're working on, the government is working on a 45Q equivalent. We have a price on carbon a year, but coupled with an equivalent 45Q will be great. We'll be able to do lots of projects. If you saw earlier in one of my map, there is a pipeline for CO2 pipeline that recently was built in Alberta. It's called the ACTL, so the Alberta Carbon Trunk Line. So along that pipeline, 240 kilometers, there is plenty of industrial sources, and at the bottom of it, there is a storage capacity available. So I believe this will be a major growth area. Around the world, I would say that what you see is a commitment by governments to put funding in place to demonstrate the technology at commercial scale. And also helping companies like ours to go through what we call the valley of death of developing a first concept and then putting it into a commercial environment. So lots of financial support taking place around the world. In Europe, the play is very different. They're focusing on storage in more saline reservoirs. So there's the concept of major hubs being developed where people would be collecting CO2 from various locations in industrial sectors, and then they'll be putting a large pipeline on land, moving the CO2 to onshore, and then there'll be a pipeline being built offshore, going deep into the bottom of the ocean, into more of a saline reservoir, for example, to safely store the CO2. So these major hubs right now are being supported by the major oil and gas, most of the partners in OGCI, and also government support will be required.
Got it.
It's building up the infrastructure.
We're going to do one more question. We have promised this to be a short interlude in your day, and we want to end promptly at 3. So I think it's a good technical question to end with. What is the purity of CO2 coming out of your system? And does it require cleanup after it goes through your filtration?
So we typically make a 95% purity, which is the minimum required for storage. And in some cases, you'll be required to remove the water, of course, to be able to compress. And sometimes there's traces of oxygen that may need to be removed depending on the type of storage that you use.
Okay, fantastic. We have one question from the group asking if you would be willing to share your slide deck with the group. And if we can talk about that later, but I wanted to make sure I addressed that.
My answer is yes on the spot. It's available to anyone.
Thank you, Claude, for being here today. We really, really appreciate it. We look forward to all of you joining future events with Innovation Stream. We have upcoming Bill Brown from Net Power. We have battery storage technologies, nuclear fusion, blockchain, you name it. We're going to be addressing this over the next few weeks and possibly longer as we're all stuck inside. Please be on the lookout for an invitation about innovation. Until next time, we will see you then. Again, please, everyone, stay healthy. Thank you all so much.
Thank you, Randy. Later.